Hello, my name is Carlos Franco, and we're going to talk about speech synthesis in Mexican Spanish using LSP as voice parameterization. Let's get on with it. You have probably came across a speech synthesis in your everyday life. For example, when you go to an ATM machine to withdraw some money, every time you ask for a direction on your GPS device, or every time you ask your phone for help with something to look up some information on the internet or something like that. This is an example.
Voz sintetizada.
The system we are using is based on another bigger system which is called HTS, which stands for Hidden Markov Models as Text-to-Speech Synthesis. The Markov models is a mathematical procedure we're going to talk about later, which is what is used to select which phonemes are needed to synthesize a phrase. As you can infer from the name, text-to-speech synthesis is a system where you can text a certain phrase, like this one here, ¿Qué tal amigos? And then you can listen to the phrase reproduced by a computer.
¿Qué tal, amigos?
¿Qué tal, amigos?
¿Qué tal, amigos?
Usually, to synthesize a phrase, we need to select from multiple phonemes, and the more phonemes we have, the more natural that phrase is going to sound. And now we're going to give some brief information about hidden Markov models. Hidden Markov models is basically a probabilistic algorithm to calculate certain probability transitions from one state to the other. In the case of speech synthesis, each state is going to be represented by a different part of the phrase. The first state is going to be the article, the second state is going to be the adjective, the third state is going to be the noun, the final state is going to be the verb. And each state has a transition probability from one state to the other, or from the same state to itself, like here. For example, if we want to synthesize the phrase El gran mago murió, which means the great magician died, we need to calculate all the different possibilities from one state to the other and from one state to itself. Here, for example, we have the article. The probability to transit from an article to an adjective is considerable, so we have 0.5 of probability. But the article to transit to itself, it's basically none, so we have no probability to transit from one article to another article. We never say it always goes to another word, like an adjective or a noun. So we go to the second state. The probability to transit from an adjective to another adjective it's quite low, so we have 0.01 of probability, but the probability to transit from an adjective to a noun is bigger, so it's 0.8 of probability. Then we go to the third state. The third state, the probability to transit from a noun to another noun, it's low, it's 0.01, but the probability to transit from a noun to a verb is high, so it's 0.9 of probability. Finally, the probability to transit from a verb to another verb, to the same verb, let's say, it's low, but the probability to finish the sentence after the verb is high, so it's 1 of probability. And then comes the period, that means end of the phrase. All these probabilities are calculated using an algorithm called Viterbi algorithm, which basically consists of multiplying each probability by itself and then by the other probability. And the higher this probability, the higher these probabilities are, they will conduct us to the right choice of a phrase. So it first calculates the probability from the beginning to the end, and then it traces back the probabilities from the end to the beginning, and the higher the probability goes, that means that this might be the right phrase one is looking for. This is how an HMM looks like in software. This is a prototype of an empty HMM. This means that no information is stored within the states. That's why it says 0 in this vector here, and the variance is 1 because nothing is stored here. But if we go to another HMM which has an A phoneme stored, we can see that the group of values here, all these values represent different variants of an A phoneme. Those values are stored within a Gaussian function like this here, and these values here represent the variance of such a function. Remember that the variance is the width of the vector. The wider this value is, the more data we have here. And now we're going to talk about voice parameterization, which is the representation of a speech signal at its minimum. What we do here when we parameterize a voice signal is that we take some samples, some minimal samples of the signal, some dots here, which are the representation of different amplitudes of that signal versus frequency, for example. So what we do here is to represent parts of the signal that will later indicate the system what phoneme we have here. So we have several ways of representation of a signal. The most popular is called the Mel-Sepsrel Frequency Coefficients, MFCC, and the proposal here is to represent the signal using line spectral pair, which is something that it's been used in other languages such as Japanese, English, but we haven't found a system that uses LSP for Spanish synthesis, so that's why we decided to test this parameterization and see how it's performed compared to the classic MFCC representation. Before speaking about the comparison between MFCC versus LSP, we're going to give a general scheme of how the system works. First of all, we need 4 different pieces of software. This is 1, this is 2, this is 3, and the last one here. First, we have a piece of software that decomposes the speech signal into 3 main elements. The software is called Speech Processing Toolkit, and the elements that the signal is going to be decomposed in are the Mel-General-Sepsrel form, which is a general parameterization that gives the user the possibility of choosing between linear predictive coding and Mel-General-Sepsrel, which is the basic parameterization we talked about a few minutes ago. Also, it decomposes the signal into its fundamental frequency, F0, and its duration. On the other side, on the front end of the system, we have another speech synthesis piece of software which is called Festival. And in this case, we're not going to use Festival to synthesize the speech, but we're going to use the system to separate a text file that we type into the computer, and Festival separates that phrase or utterance typed into a label file. That label file contains basically that what it contains is basically the different, it decomposes the utterance in its different phonemes. So we can indicate the system which phonemes are going to be used to synthesize a certain phrase. So that label file it's also fed into HTK. HTK is a system that calculates hidden Markov models. It stands for Hidden Markov Models Toolkit. And what this software does is to produce that Viterbi algorithm we talk about to make the phoneme selection needed. Once that we have the required phonemes, we go to another piece of software which is called HTS Engine, which consists of two sound sources. One of these sound sources is used to produce the voiced sounds, which are those sounds that come from vowels like A, E, U, O, etc. And the other voice source, is used to produce those unvoiced sounds, which are the sounds produced when we pass the air through the vocal tract. Like, for example, every time we make an F or an S, you can feel the air coming through your teeth. That's an unvoiced sound. And the sound, it kind of resembles that sound of a white noise source, like s or f. It sounds a bit like that, doesn't it? Finally, we have the synthesized speech that we required. Now we're going to speak about the maths behind it. We have here the equation of a linear predictive coding signal which represent speech. The sum of all these A coefficients are basically a representation of a speech signal delayed in time. All these coefficients are part of this LPC coefficient function. Every time we spread this summatory here. And LSP is defined by two polynomials, P and Q, which contain all these coefficients, which are added and are also subtracted within each other, but with a delay, with a time delay. And this definition is what allows us to represent those coefficients with a signal amplitude versus frequency. And we can also take those coefficients to reproduce that sound. That's what we do basically. These are the results of the comparison we performed between MFCC and LSP. We had to have an external opinion about LSP, so we carried out a series of MOS tests, or MOS tests as some people call them. And we chose a population of 30 listeners. Each of them listened to 5 phrases in 3 versions. They first listened to the original voice. Then they listened to an MFCC synthesized phrase, and finally an LSP synthesized phrase. And they had to qualify them from 0 to 5, being 0 the worst and 5 the best. And we can see through these results, we qualified 2 aspects, naturalness and intelligibility. We can see from the results here that naturalness had a better performance in LSP than it had on MFCC, and also intelligibility. What we took for let's say what made us take the decision that LSP was the best choice was the variance among the qualifications given by the listeners. MFCC has a bigger variance, that's 0.42 in naturalness and 0.59 in intelligibility. For this reason, we consider using LSP in future voice synthesis, which this means is that the listeners were less consistent when qualifying MFCC, and they were more consistent when giving the qualifications to LSP.
Pero no se puede escapar si nos precipitamos.
Pero no se puede escapar si nos precipitamos.
Aprendí bien pronto a conocer mejor esta flor.
Aprendí bien pronto a conocer mejor esta flor.
Su información, querido amigo, no tiene precio.
Su información, querido amigo, no tiene precio.
El deseo se dice del anhelo de saciar un gusto.
El deseo se dice del anhelo de saciar un gusto.
Ahora sí, me dije, todos van a voltear a mirarnos.
Ahora sí, me dije, todos van a voltear a mirarnos.
What you could listen to in the last part is the original voice first, followed by the synthesized speech using LSP. You could probably notice that it resembles a lot the original speaker, but still further work needs to be done to achieve a synthesized phrase which results undistinguishable from the original speaker. And some final comments. We can confidently say that LSP surpassed MFCC, so we will be using LSP as the preferred method of speech parameterization. We need to mention also that HMM is not state-of-the-art in phoneme selection. The people in speech synthesis are using DNN now, but not enough information is available, so we need more information to have a fully functioning speech synthesizer like the one we have now using HMM. So we need to wait to see what happens with DNN applied to speech synthesis. And finally, we had some commercial proposals of the system we just presented here, so let's see what happens there. So that's it. That's basically it. That's what I have to share on LSP. I hope you enjoyed the presentation. Any questions, please email me at francocarlos@gmail.com. Thank you very much for your attention. See you later.